methods of cryptography. So here is going to be a little bit of an overview, and hopefully by the end of this presentation, we'll have answered all of these questions about cryptography for you. So the first couple are going to be, what is matrix-based cryptography and how does this relate to banking? So those are going to be kind of about the more basic methods and the past methods that we used to use. Then we'll move on to why don't banks use basic cryptography anymore? And after that, we'll move forward to some of those more advanced techniques, which are modified Hill cipher and advanced encryption standard. Okay, so what is matrix-based cryptography? So the International Organization for Standardization defines cryptography as the techniques and algorithms that are used today for secure communication and data storage. So when we're talking about matrix-based cryptography, at least at first, at the beginning, these couple slides, we're going to be talking about purely matrix-based cryptography, which means those techniques and algorithms that they talk about for cryptography, we're going to be talking about them using matrices to do that. So that little infographic on the left there is kind of like the life cycle of how this works, right? So we have the message is written, then it's going to be, or with the data or whatever we're using, then it'll be encoded with a key given out, and then it's going to be decoded with a private key, and then the message is read by the individual receiving it, or the data is received by whoever's supposed to be receiving it, right? And that's going to be how public key cryptography works. There are 4 main types of cryptography, but we're really only going to be talking about public key cryptography today.
So we have a video behind the math that involves cryptography. So we're going to talk about the video.
Here are the matrices we will use for our example. Now, we will assign each letter of the alphabet a number in order. For example, A would be equal to 1, B would be equal to 2, and so on. A space or a break will be assigned the number 27 because there's only 26 letters in the alphabet. Now, we translate our message into these numbers, as you see below. Now that we have our translated code, we need to put these numbers into vectors. Since we are using a 3x3 matrix, we break the enumerated message above into a sequence of 3x1 vectors like so. Note that it was necessary to add 2 spaces or 27s at the end of the message to complete the last vector. We now encode the matrix by multiplying each of the above vectors by the encoding matrix. This can be done by writing the above vectors as columns of a matrix, and then perform matrix multiplication of that matrix with the encoding matrix like so. The columns of this matrix give the encoded message. The message is then transmitted in the following linear form. To decode the message, the receiver writes this string as a sequence of 3x1 column matrices and repeats the technique using the inverse of the encoding matrix. Thus, to decode the message, they will perform the matrix multiplication and receive a matrix that should look familiar to you. The columns of this matrix, written in a linear form, give the original message. And now, you can meet in secret with confidence that no outsiders to your conversation will ever be aware.
So talking about the video, there are also a lot of applications in banking related to matrix-based cryptography. So the first one that we have is how we can secure quantitative finance and algorithmic training models. So in quant finance, the big firms such as Jane Street, JP Morgan, Citadel, they rely heavily on matrix-based encryption to secure their trading algorithms, because in high frequency trading, speed is a really important factor, and matrix multiplication is highly optimized for parallel computation. So in this case, it really helps these large firms to optimize their trading frequency algorithms, and at the same time use matrix-based cryptography so that it is not cracked or broken by the competitors. Not only that, we also have encrypting the encryption of customer data, because when a customer is initiating a wire transfer, there is a lot of factors involved, such as the bank account number, the routing number, the amount, etc. And that kind of information is sensitive, which can be traced by hackers and can be a problem. So to solve this, what banks do is they group this data into data blocks, and in like terms of vectors and stuff, where this is as an input standardized into different state matrices. Then they apply linear transformations to completely transform the data before it's sent into the cloud. And this transformation is critical so as a first line of defense before the data is sent to the cloud so that there is lesser chances of getting the systems hacked or the data breach. Not only this, the final matrix-based feature that I would be talking about is secure interbank communication. At a macro level, a lot of global financial networks depend heavily on interbank communications on matrix-based cryptography. One of the example is Swift transfers. So in order to do this and keep it safe, the networks employ advanced cryptography key exchanges where the keys are shared between the sending and the receiving bank such that when a transaction or any sort of transaction is initiated, the receiving bank has the exact corresponding inverse operation as the person was talking about in the video, where it can verify the sender's identity and reconstruct the whole instructions immediately.
So why don't we use the simple matrix cryptography anymore? The one rule flaw. It explains that a simple matrix ciphers used by a fixed mathematical rule. This is dangerous because if an attacker cracks just one word, they can reverse engineer the entire message. The mobile limitations. So mention that older certificate systems are too heavy for the phones, meaning they drain mobile batteries and use too much power. So the cost of failure, the point is a Capital One breach. In 2019, a single hacker compromised the data of over 100 million people, proving that the outage security has massive real-world consequences. So the modern solutions for the banking security. So first is certificate-less cryptography. This is a newer approach that uses efficient matrix-based key generation, specifically designed to protect mobile processing power. And second is modified Hill cipher, which is MHC. This keeps the mathematical elegance of a Hill cipher, but adds extra protection against the attack. It uses a double lock system to make the code significantly tough to break, and the AES, Advanced Encryption Standard. So it briefly introduces the Advanced Encryption Standard. It is the global standard used by banks and governments today to ensure that the data remains unbreakable.
So essentially going more into detail about the modified Hill cipher, it is essentially a more enhanced version of the traditional Hill cipher, which was essentially what we learned earlier within the presentation, which was about encrypting and decrypting messages instead of just using each letter being encrypted. We group the letters together and have them be transformed using matrix-based multiplication. Now, unfortunately, this led to the lack of development, which also lead to more attacks, mainly being the plain text attacks, which left the systems very vulnerable. So instead, they developed the modified Hill cipher, which provided that little extra layer of security, which include modifications such as the key-dependent permutations, the initialization vectors, and basically combining other cyber techniques. And so here's a simple example of comparing the standard and the Hill cipher, the modified Hill cipher. So essentially, we see that on the left, you encrypt the message, but you have to put it through a single matrix in order to get your ending text. While with the modified Hill cipher, you get to encrypt it in two different layers, which builds that double lock security system that prevents attackers from solving the multiple unknowns that they have to figure out.
All right, I'll take you through a quick example of the modified Hill cipher. So we start with the 2x2 matrix, and through a series of calculation, our plaintext high maps to the numbers 7 and 8. Now, this is what we do differently in modified Hill cipher. Before we multiply, we add an initialization vector to the plaintext, and that one step means identical messages encrypt differently every time, which is the key improvement over the classic Hill cipher. So basically, we run the matrix multiplication, reduce mod 26, and our text high becomes off in the modified Hill cipher. Moving on to the next slide, we'll talk about the Advanced Encryption Standard, which is a global encryption standard used in banking, government, and even our browsers every day. It works on 128-bit blocks and supports 3 key sizes. each adding more rounds for extra security. So encryption starts with an initial add round key where the plain text is mixed with the key, then each round runs 4 steps. Subbytes, shift rows, mix columns, and add round key. And the final step skips mixed columns and outputs the ciphertext. We'll learn more about these steps in the slides that follow.
So moving to maths behind AES, where is the linear algebra? So AES loads your data into a 4 by 4 matrix called the state matrix. Every round runs 4 operations on it. 3 of them are linear algebra, matrix multiplication, matrix addition, and permutation. The big one is mixed columns. It multiplies each column by a fixed matrix, that is exactly AX equals B from our class reference. Moving on to next slide, which is AES example mixed columns. So mixed columns takes one column from the table, treat it as a vector, and multiplies it by the fixed matrix M. Every output bit depends on all 4 input bits. So changing one input changes the whole column. It is just same as the matrix times vector. Moving on to our conclusion, to wrap up, Bank started with simple matrix encryption like Hilkeffer, then modified it by adding some more complexity. And today, EES uses a 4 by 4 matrix column across 10 rounds. Every generation use same core idea matrix. Linear algebra is the ultimate maths behind modern banking security. Moving on to the next slide. This is our work distribution for our presentation. And then we have our next slide as references that we used. And that's all for the presentation. Thank you, everyone.